Today we're going to take a look at section 1.2, which is exploration with patterns. When I was in grad school, when you do a PhD, you have to do something called a dissertation. A dissertation is like writing a book, and it's part of getting your degree. One of the things that I did in my dissertation is I had two people that I was doing like case studies on, and they're teaching. And I asked them the question, what is math? One of my people said mathematics is the study of patterns. And I think to a great extent that's really true. We look for patterns. We look for patterns in all sorts of ways when we're problem solving. And interestingly enough, the other candidate said mathematics was problem solving, which is what we were doing in section 1. So we're going to take a look today at some patterns. So just some vocab so that we are all talking about the same things. A conjecture is a statement or conclusion that has not been proven. Similar to a hypothesis. It's what you expect to happen. It's what you believe is happening. That's called a conjecture. A counter example is an example showing that the conjecture is false. So you're proving that it's not true. And there are two types of reasoning that we're going to talk about, inductive and inductive and deductive. Inductive reasoning is a method of making generalizations based on observations or patterns. So you've done inductive reasoning before. In fact, probably everybody did it this morning. Maybe not everybody, but raise your hand if you checked the weather before you got dressed this morning. About half of you. So how did the other half of you decide what to wear? Okay. And part of that also is usually because it was hot yesterday and it was hot the day before, right? So you made the assumption that it's probably going to be hot today. I usually have the problem with rain. It catches me off guard every time because I don't check the weather very frequently. So that's the one that catches me off guard. But we make decisions based on previous experience a lot, and that's called inductive reasoning. Okay, when we make it based on what has previously happened. Deductive reasoning is the use of mathematical axioms, theorems, definitions, or undefined terms assumed to be true and logic for proof. So it's making a guess of how much money you're going to make because you already know what your pay rate is and you know how many hours you worked. It's not really a guess, is it? You know. There's an equation. You can do it whether there's actually a written down equation or not. You know how to figure out your own income or how much money you're making. Right? There's a concrete way to do that. Now, it doesn't mean you won't make a mistake. You can still be wrong. But there's a concrete way to do that. That's called deductive reasoning. Okay? Sequences. Sequences are an ordered arrangement of numbers, figures, or objects. Children work with sequences really, really young, like pre-K. So those of you, raise your hand if you're one of my early childhood folk. About half the class. Sequences are big time stuff. I remember them in the materials my kids used to bring home, right? It goes red square, blue triangle, red square, blue triangle. What comes next? That's a sequence. It's recognizing a pattern. Okay, so sequences don't have to be numbers. We're going to be working with numbers and what we're talking about, but sequences are actually much more broad. A recursive formula is a formula based on the pattern established after one or more consecutive terms are given, and a rule that shows how to obtain each successive term of the sequence. So let me give you a numerical example. Let's say that we have an example of numbers, and the example is 3, 5, 7, 9. And it keeps going after that, okay? The pattern is that I add 2 every time, right? That's the pattern. Well, knowing that the pattern is add 2 every time, that's this rule that we figure out to get the next term business. The only way that I can still know what I'm doing is to know where I am in the sequence. Like I can have a rule add 2, but if I had a rule add 2 and I want to know what term comes next, I need to know what term came before, right? Just knowing the rule is add 2 doesn't really help me. It's not enough information, okay? So that's a recursive formula. I need to know where I am in the pattern already, and I need to know how do I get to where I'm going. An nth or a general term, and I will tell you right now, I use these interchangeably. I don't even remember which one your book uses. But if I'm talking about an nth term or I'm talking about a general term, that's the same thing. This is actually a formula used to create the nth term in a sequence with no prior terms needed. This is like more information than the previous one. You don't need to know where are you in the sequence. You don't need to know what pattern's happening. Basically, you're dealing with something where you have an equation that tells you how to get what you want. Okay, and we'll do an example so you can see that one, because that one looks a little bit more concrete with some examples. All right, specific types of sequences. We're going to look at 2 today, I think. The first one is called an arithmetic sequence. This is a sequence in which each successive term is obtained from the previous term by the addition of a fixed number. Now, please understand the fixed number could be negative. So it could kind of look like we're subtracting, right? Just adding a negative. So I gave an example a moment ago. I'll write that one in this time. 3, 5, 7, 9, and we said that the pattern was adding 2. So this pattern is plus 2. I get between terms by adding 2. The number that I add every time is actually called the common difference. It's the fixed number added to previous terms to get successive terms. The common difference, I mentioned it, and I'm going to mention it here again, that this could be positive or negative. So if it looks like I'm subtracting 7 every time, I'm not really. I mean, I am, but I'm adding a negative 7. So the common difference would be negative 7. Another really common type of sequence, is a geometric sequence. So in a geometric sequence, this is a sequence where you obtain the successive terms by multiplying by a fixed number. So let's say, for instance, I had 3, 15, 45. Did anybody notice what I multiply each time by? By 5. 3 times 5 is 15. I'm sorry. Yeah, I said that right. I screwed it up. I was doing off the cuff. That's what happens. Somebody tell me this is what I was trying to do. Tell me what 15 times 5 is. Is 75? Okay, 75 is what I want there. My bad. That's what happens when I'm writing down things that are on my paper. 75. It's times 5. So this number that we multiply by is called the common ratio. And it doesn't have to be a whole number either. It could actually be a fraction. So let me give you an example of a fraction so that you can see what I mean when I say it could be a fraction. Okay, so these numbers are going down, right? They're going down each time. By how much? I mean, like, what's happening in terms of the decrease here? What do you see? It looks like it's division, right? It looks like I go from here to here and I divide by 3. But did you know that multiplication and division are actually the same thing? Please don't tell a third grader that. There's no reason to, burst the bubble. Okay, let them believe they're different. I'm really, really good at multiplication. I stink at division, whatever, okay? Just let them have their moment, right? So they're really the same thing. So what do I mean by that? Well, this says that we're dividing by 3. But have you ever seen it written like this before? We write it that way for division. I mean, we can, right? In a fractional form. But if we're willing to write it in a fractional form like that, it's really the same as writing it also like that. And all of a sudden now the division actually looks like multiplication, but it's multiplication by 1/3. How are 3 and 1/3 related? Do you remember what they're called? They're reciprocals. So if it looks like there's division going on, that's okay. It just means you're multiplying by a fraction. The fractional part of what we're looking at, 1/3. So the ratio here is not 3. The ratio here is actually 1/3 on this problem. Okay? Oh, we are going to get to one more type of sequence. I wasn't sure if we hit that here. Okay, one more type of sequence. We won't dwell very long on it, but this one's kind of a fun one. Show of hands, who's heard of a Fibonacci sequence before? I'm not going to promise it. I'm not going to ask you to tell me what it is. Just have you heard of it? Okay, several of you have. A Fibonacci sequence is non-arithmetic, so that means you don't add to get to the next term. It's non-geometric, which means you don't multiply to get to the next term. But it follows a different pattern. Something is not one of those two things, and it's common in nature. You actually see it in the tree rings. I can't remember how that exactly works, the exact application, but it's found in the tree rings. It's also found in the way that seashells are formed, specific types of seashells, Fibonacci sequences. So let me give you the Fibonacci sequence. And if you know the pattern, mum's the word. Let your classmates take a look at it and see if they can figure out what the pattern is before we continue. So this is the Fibonacci sequence, at least the first few terms of it. Take just a minute to look at it and think about what you're seeing. Can someone tell me what the next term should be after 21? 34. Okay. What would come after 34, Alicia? Did you have 55? What would be after 55? 89? Okay. So who would like to share what's happening for the rest of everybody who's going, where'd those numbers come from? Okay, go ahead.
You add the number that's before okay, I know what's going on. It's like with 3 and then 5, you add the 2 to the 5. Or to the 3 to get the 5.
Okay, circle the ones you're talking about. So if I were to add 2 plus 3, I would get 5.
Plus 5.
And then 3 plus 5 would give me 8. So if I wanted to do, just for the sake of saying we know what we're doing now, what would I have to do to get the number that comes after 89? I'd have to add 55 and 89 together to get the next term that comes here. Okay, so that's a Fibonacci sequence. It's not arithmetic. It does include addition, but it's not just adding this constant number every time. Okay, so every time I teach this, I always feel like this is the bizarrest place to put this, but I need it in a minute, and I want to make sure everybody remembers it, okay? So this is the definition of powers. So the definition of a to the n. If n is a natural number, then a to the n is a times a times a times a, da 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 da, n times. If n is equal to 0, and the a is not 0, then a to the n, essentially a to the 0, would be 1. We're not talking about negatives. It's not in our vocabulary at the moment, so don't worry about those, okay? We're only dealing with positive numbers. Whole numbers is our well, we're going to hang out with whole numbers till we get to the end of the semester, and then we'll get to some negatives, okay? All right, we are going to take a look at an example of a sequence and try to figure out if, in fact, we have a specific type. All right, we've got 2 examples here. So the first one is 1, 4, 7, 10. There are 3 things we're going to do on each of these examples. We're going to list the next 3 terms. We're going to decide if it's arithmetic, geometric, or neither. And then we're going to find the nth, or general, term of the sequence. So, number 1, letter I, is usually the easiest part. Pattern is 1, 4, 7, 10. Without saying anything to your neighbor right now, write down what you think the next 3 terms are. What would come after 10? Don't say anything. Just write it down. Okay, turn to somebody nearby and see if you chose the same 3 numbers. Anybody nearby you? Make sure you speak with someone. Everybody should be talking. Okay, what did we get? 13, 16, 19, which means you guys recognized a pattern that was what? Adding 3, right? Did everybody recognize that this is an adding 3 pattern? Fabulous. If you recognized, which you did, that this is an adding 3 pattern, this is I, an adding 3 pattern, then you should be able to answer part 2 very quickly. Is it arithmetic, geometric, or neither? It is arithmetic. Absolutely. Arithmetic means I add the same number every time. We would call the number 3 our common difference. That's what we would call it. Now, step 3 is the part where I always lose people, and I don't mean to, I promise. So I will tell you that there is a method in your book that I don't use for this, and there's a reason for it. And I would prefer that you not to. In order to use the method in the book, you're going to have to actually memorize a formula. And the reality is that if you ever need to do this in the future, you're not going to remember the formula. Agreed? Yeah. I mean, you're not. You're not going to remember a formula. So I don't like to force you to try to memorize formulas that you're going to forget anyway. I think that's kind of a waste of all of our time. What I'd rather you do is to think about what's really happening and generate something from there. So let me think through with you how this works. We have 3 added multiple times. 3, add 3, add 3, add 3, add 3. Now, when we talked about Gauss, we decided that adding, his number was 101. Adding 101 plus 101 plus 101 is very tedious. And you know a quicker way to add something where it's the same number multiple times. You called it multiplication. Okay? So that 3 that we got, we don't want to add 3, add 3, add 3. We want to multiply by 3. Make sense? Now, I don't know how many times I want to multiply by 3, so it's just going to be 3n. Okay? Maybe I multiply by 3 4 times, right? Maybe I've added 4 3s. Maybe I've added 10 3s, so I multiply by 3 by 10. That's what the n is there for, because I don't know how many times I'm going to be multiplying by the 3, okay? Or adding the 3 to be a multiplication factor. But here's the catch. If I put in if I put in n equal to 1, which should mean the first term in my sequence, I would have 3 times 1. And 3 times 1 is 3. Is the first term in my sequence 3? No. What is it? It's 1. I want it to say 1. I don't want it to say 3. I want it to say 1 when I do that. So here's the cool thing. Are you ready? I'm just going to take the 2 away. I don't need it. So let's try it over here again. If I erase what I just did, and I take 3 times 1 minus 2, do I get my 1 now? I do. And I know it almost feels like I'm cheating to do that, right? I just put in a minus 2. Like, how can I get away with that? Well, I'm resetting the beginning of my sequence. And you can check to make sure it really works. Let's try just the next term and see what happens. What happens when I take 3 times 2 minus 2? Do I get 4? That's what I'm supposed to get. We'll try one more just to say, you know, I'm not pulling your leg. How about 3? What's 3 times 3 minus 2? It's 7. This number always trips people up. But all it really is adding or subtracting whatever you need on the end to make it equal the first number. That's all it is. And this is how we treat arithmetic sequences. Which must mean that B is not, right? Got to do something different. I'm not going to do the same thing twice. What do you see for your next 3 numbers here? Again, don't say anything. Write down what you think they are. Grab a calculator if you need it. What comes next in this sequence? Turn to a neighbor when you're done. Check and see what they have. Okay, what'd you guys get? What's after the 24? 48, and then 96, and then 192. Whoops, 192. There we go. Okay, so that's I, right? Finding the first 3 terms. So what pattern did you notice? Multiplying by 2. Fantastic, which makes this a what type of sequence? Geometric. And of course, I chose one that was arithmetic and one geometric on purpose, in particular because I wanted to show you what we do when we find the nth term. How does that work? Well, it actually goes back to this weird definition that showed up on the bottom of the screen. Where'd that come from? Well, just like on part A, when we talked about the fact that when we add 3 multiple times, that's really just multiplication. When I multiply by 2 multiple times, that's really just an exponent, right? 2 squared means 2 times 2. 2 cubed means 2 times 2 times 2. 2 to the 4th means, you get the idea. This is exponents. That's what happens in a geometric sequence. So what does it look like? Well, it looks like whatever you've been multiplying by to that exponent. 2 to the n. Almost. Almost. There's a couple of problems with that. You see, it didn't really start at 2, it started at 3, right? If I put in n equal to 1 here, that's no good. And I can't just add or subtract onto this. It doesn't work like that because it's geometric. It doesn't just shift it by an addition factor, it's shifting it by a multiplication factor. So I can almost get what I want if I multiply by 3. So let me show you what I mean by that. I started this sequence with a 3, right? So I should start this pattern with a 3 as well, with the general term. It should be 3 times this. But what happens if I put in n equal to 1 here? What do I get? I get 6, which isn't my first term. But what is it? It's my second term, isn't it? I put in n equal to 1 and I ended up getting my second term. And sure enough, if I tried again, let's put in n equal to 2 just so you can see. If I do 3 times 2 squared, what will I get? I get 12. That's not my second term, it's my third term, right? So how do we compensate? How do we fix it so that it really gives me the correct term in the sequence instead of, one term bigger? Well, all I got to do is subtract 1 in the exponent, and that'll fix it. Now, the reality is your exponent's always going to be n minus 1. It's not something special to this particular problem. It's always going to look like that. But the reason it's going to happen is because of what I just showed you. If I leave it as n, I get the second term instead of the first term. I'm off by 1 in terms of where I am in my sequence. This will fix it. So let's take a look, okay? So let me do this down here now. So if I take this now and I do 2 minus 1, what is, I didn't mean 2 minus 1, 1 minus 1, 1 minus 1. What is 1 minus 1? 0. And over here, I reminded you of the fact that 2 to the 0 is 1. And then 1 times the 3 in front of it would give me 3. And then down here, I have 2 minus 1 as the exponent. 2 minus 1 is 1. 2 to the 1 is 2. And 2 times my 3 at the beginning is 6. So it just, that minus 1 in that exponent just shifts it back to get me located on the right term to start with. Now, here's the question. We had 2 types of reasonings. Flip back and read them. Is this inductive or is this deductive reasoning? Look back at the definitions and see what you think it is. Which one do you think it is? Somebody bold enough to guess. It's a 50-50 shot, right? It is inductive. Very good. Inductive means we take a pattern and we try to guess what happens next. That's my weather example, right? The pattern is it's been hot, 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 hot. Chances are it's going to be hot tomorrow, folks. Just going to say. I'm not going to check the weather. And if it's cold, I'm going to wish I did. But that's the pattern, right? It's looking at the pattern. That's what we've done here. We've looked at a pattern and we've tried to make generalizations. Are our generalizations good guesses? They're good guesses. Are they for sure right? No. Just like it's a good guess it's going to be hot tomorrow, but it may not be right. All right? Okay. Let's take a look at one more example before we leave. Example number 2. This question asks the question by starting with the general term. Using the nth term, the general term, find the first 5 terms of the sequence and then decide, arithmetic, geometric, or neither. So, we're going to let n equal to 1, n equal to 2, n equal to 3, and see what happens. So if n equals to 1, I would have 5 times 1 plus 6. What is my first term? It's 11. What if n equal to 2? It's 16. How about n equal 3? What is it? It's 21. Right. How about n equal to 4? $26, and n equal to 5 will be our last one. $31. Okay, so those are our first 5 terms. 11, 16, 21, 26, 31. Can you tell if it's arithmetic, geometric, or neither? It's arithmetic. How do you know? There's a couple things you could say. Yeah, if you look at the pattern you just created, it's adding 5 every time. What if you look back at the equation that we started with? Not equation, but the expression we started with. It's the arithmetic pattern that I gave you from the one before. You're exactly right. 5 times a number. It means I'm going to be adding 5 every time. And the 6 at the beginning has to do with where I'm starting from. Right, how to get that first starting value to be the right one. It's arithmetic. Let's try the next one. N equal to 1, so this is 1 squared minus 1, which is 0, yeah? N equal to 2, 2 squared minus 1 is 3. N equal to 3, 3 squared minus 1, 8. N equal to 4, 4 squared minus 1, 15. I was supposed to say 15. N equal to 5, so 5 squared minus 1, 24. So I've got 0, 3, 8, 15, 24. Is it arithmetic, geometric, or neither? Are you both saying neither? You don't know? You said neither. Neither. It's neither. If you think about addition, I would have to add 3 to get from 0 to 3, but I would have to add 5 to get from 3 to 8, right? It can't be geometric because there's a 0. I can't multiply 0 by anything and go anywhere. So this one is neither. Is this inductive or deductive reasoning? This one's deductive, okay? It's deductive. I know beyond a shadow of a doubt, unless I made a mathematical, like computational kind of error, that's not logic, that's, computation. I know beyond a shadow of a doubt that that pattern is correct because I started with an expression that I evaluated. Plugged numbers in, got solutions out, right? Plugged numbers in, got values out. I didn't have to do any guessing. I didn't have to speculate that the pattern would continue the same way. I know it will because there's a pattern, an equation or expression given to me that says so. Now, we're going to actually start with this 0, 3, 8, 15, 24 next time. Remind me if I forget. There is a pattern here, and I want to show you what it is because it relates to some of the homework problems you have, but it is not arithmetic or geometric.